Hi guys, so today in this video we will demonstrate and discuss about the Homo Lumo energies. Okay, so we will be running a Mopac calculation for a molecule and understand the concepts behind the Homo Lumo energies and how this determines the property of a molecule. Okay, so we'll get into the details about that. Before that, you see a picture over here, right? It's the molecular orbital for your hydrogen molecule. Okay, so it has two electrons involved in bonding, so it is found in your HOMO orbital and the LUMO is empty. Okay, and you see that there is a certain energy gap which you call it as your Homo Lumo energy gap, and this gap determines the excitation of the electron from HOMO to LUMO when you supply a suitable radiation, a source of radiation. Okay, where you see the HOMO and the electron is excited to LUMO. So your HOMO LUMO energy gap plays a major role in predicting the property of a molecule. Okay, so now so one important concept which you have to understand while you study about the Homo Lumo energy is that about the quantitative structure activity relationship, which is known as the QSAR. Okay, so what this actually mean? Okay, this is completely related with the ligand structure based drug design, right? So this is similar to your docking studies. Okay, exactly, the docking studies where the drug's potency or toxicity with variety of molecular descriptors is related and studied in your quantitative structure activity relationship. Okay, what are these molecular descriptors used to relate the drug's potency or toxicity? Yes, so there are many descriptors available. One such descriptor is the number of hydrogen bond acceptors, right? So this can be easily calculated based on the molecular connectivity, that is the bond orders. Okay, but there are other advanced descriptors available which will require some more advanced calculations, and that can only be computed. You cannot use a pen or paper to do this. Okay, so you need some advanced calculations, and that calculations needs the help of quantum mechanics. Okay, so one such descriptor is your Homo Lumo energies, which relates the chemical reactivity of the drugs. So the descriptors that may relate to chemical reactivity of drugs such as Homo and Lumo energies must be obtained from the quantum chemical calculations. Okay, now so let's understand what HOMO and LUMO energy actually mean. We know that HOMO is the highest occupied molecular orbital and LUMO stands for the lowest unoccupied molecular orbital. The name itself, the expansion, explains the idea about the orbitals. Highest occupied represents it is the orbital where the probability of finding electron is more, but lowest unoccupied represents that there is no electron present, the orbital is nearly empty, right? Okay, what information actually you get from these two orbitals? According to the frontier orbital theory, you notice that the nucleophilic attack occurs only when the electron flow from HOMO to the LUMO. Why? You know that HOMO is the occupied level, right? So you have electrons in that, and you can call the HOMO nearly as a nucleophile, and the LUMO you can call nearly as an electrophile since it is electron deficient. Okay, this is the concept about the nucleophilic attack about the HOMO and LUMO according to frontier orbital theory. In stable molecules, you can notice that the occupied electrons will always reside on the orbitals with negative energies. That's why most of your HOMO energies are always negative or mostly negative because it's occupied with the electrons. In case of your LUMO, which is the unoccupied orbital, will have positive energies. This can be visualized and you can see all the calculations available when we do the Mopac demonstration. Okay, then what this HOMO and LUMO are related to the reactivity of molecule. How the energies of these two orbitals are related to the reactivity of the molecule? Yes, you can see the occupancy of the electron will determine the reactivity of the molecule, and that results in the energy of the HOMO and LUMO. You know that the HOMO level is found near zero, right? So you can call that if HOMO is pretending to be a good nucleophile, then it will not cause much because it's near zero, and if the LUMO is also near to that zero, the electron transfer will take place very easily to make a new bond. So it will not cost that much of time or nothing. Okay, it's not going to affect anything. Since your HOMO LUMO gap is small, so if it is near to zero, it will make your HOMO be a good nucleophile and your LUMO will be a good electrophile. Okay, this is the thing which you have to notice, a very important thing. So your HOMO is a good nucleophile when the electron transfer is easy. Your LUMO is a good electrophile when the electron is accepted very easily. Okay. For some large molecules, if you see, we do the ab initio quantum mechanical calculations. Okay, so we saw that when you go for larger molecules, if you are using other molecular descriptors like the HOMO LUMO energies, you find it difficult to calculate with your pen or paper, or you cannot do the calculation. Instead, you would require a computer to do the calculation, right? So you see that the ab initio quantum mechanical calculation will give you accurate results, because the term ab initio means from the beginning. So it will consider all the core electrons. It will consider almost all the core electrons and calculates the entire property of the molecule. Okay, that is a very good result which you get, but it is time consuming. So it takes a lot of time. Mostly the ab initio calculation and DFT calculations are carried out in your Gaussian. It is a the software is not free. It is a commercial software program. Okay, so normally everyone cannot use that because it costs very much, too much. Okay, so since it's time consuming and a commercial program, we go for to get the QSAR studies with some other available softwares. So one such calculation is that we go with the semi-empirical calculations, where you can find that it is closely related to the ab initio. So the results which you get in ab initio is closely, okay, it's quite accurate in your semi-empirical calculation also. So you cannot say it's not equaling the ab initio. Moreover, it is giving more accurate results, okay, in the semi-empirical calculations. So you would have been aware about the Hamiltonians used, right? There I have explained about the semi-empirical model, the NDDO model, which is used in Mopac to run the calculations, right? So see, so it will give you the reasonably good descriptors for your QSAR studies in a fraction of a time. You can see your Mopac programs will run in fraction of a time, right? So you can use several free programs, that is your Mopac, and you can visualize in gammas, but here we will be visualizing your HOMO LUMO energies and molecular orbitals using JMOL. Okay, let's try with that. Okay, these all softwares will allow the semi-empirical calculations. Okay, this one sort of research work which has been done by Skulls and his co-workers, which link the toxicity to two molecular descriptors. Okay, here we will discuss about the two molecular descriptors mentioned here, that is the hydrophobicity and the electrophilicity. Okay, I'm not going to discuss about this because I'm not dealing with this here. Now I'll discuss about the electrophilicity, which is related to your HOMO LUMO energies. Okay, you can see that the electrophilicity is numerically characterized by the energy of the lowest unoccupied molecular orbital. Okay, so you know that your LUMO is an electrophile, right? So the electrophilicity is completely characterized only by the LUMO. Nucleophilicity is completely characterized by the energy of the HOMO. See, with this you can get the details about whether the particular molecule is prone to your nucleophilic or electrophilicity, like that. Okay, so the LUMO energy can only be predicted using the quantum mechanics, right? So the results of the quantum mechanics depends on certain approximations. Yeah, we discussed it already, all the approximations which has done. In this research work, the authors have used AM1 semi-empirical model. Okay, so they have used AM1 semi-empirical model and run a Mopac program, and they have found the details about the toxicology studies. They have done the toxicology studies and properties of the drug. Okay. Yeah, now what this Homo and Lumo gap, and how does it change the property of a substance? A very important thing which you have to notice over here, right? So let us understand what is Homo Lumo gap. Okay, see, the Homo Lumo gap is where most likely excitations can occur. Okay, only when the excitations occur, the bond connectivity will happen between two molecules, and the reactions are possible, right? So the excitation occurs more likely only in between the Homo Lumo gap, right? So that gap must be considered and should be given some importance, more importance, right? For example, I'll take large aromatic systems. For large aromatic systems, the Homo Lumo gap is very small. So what this brings the significance is that when your Homo Lumo gap is very small, the electronic excitation, that is the electron jumping from the Homo to Lumo, that is from lower energy level to higher energy level, is very good. It happens in very faster rate, and what happens as a result, when you have the greater mobility of the pi electrons in large conjugated pi orbital system, the greater the distribution of the energy throughout the molecule. See how greater your mobility of pi electron is from Homo to Lumo, that much the energy is distributed in a high level throughout the molecule, and your molecule is highly stable. It is highly stabilized. Right, so thus we conclude that the Homo Lumo gap will correspond to better stability. So this is the way how the Homo Lumo gap changes the property of a substance. See, a very important property, that is the stability of a molecule, is only determined by the Homo Lumo gap. Only when a molecule is stable, you can subject it to further process, right? So without a stable molecule, you can't carry out any further reactions. So this information is excellently obtained from the Homo Lumo gap. Yes, this is one sort of research work which has been done. Okay, you can see that procaine is an anesthetic drug. Okay, it is used as a local anesthesia, either topically or intravenously. They'll give through injections also, or through oral they'll take it. Okay, it's an anesthetic drug, but they found that the procaine drug is found to have some anti-cancer activities. Okay, so what they did is they did some docking studies, that they made an interaction of that anesthetic drug, the procaine, with our DNA. Okay, they did this docking studies, and before that they had an excellent information from the Homo Lumo energies to confirm this, right? So what they did, you see, for procaine they found the Homo Lumo energies, it is found to be 3.124. when you subtract the Lumo energy and Homo energy, you get this value, delta E, the Homo Lumo energy gap. And see, this is adenine, cytosine, guanine and thymine, which are the DNA bases, right? So if you see adenine, it has the Homo Lumo energy gap as 3.879 atomic units. Then you see for cytosine it is 3.4, and you see for guanine it is 3.69, and see for thymine it is 3.84. See, almost you can see that the energy gaps for all these, the drug and the DNA bases, are almost same. So the electronic excitations are very similar, are very close, right? So with this they conclude that this particular drug has some anti-cancer activities, and the mechanism of the interaction between this drug with the DNA was determined. See, they get the data about the charge transfer also. So charge transfer, the electron transfer occurs, and which results in giving you these values. Okay, with this they got some excellent information. See, so the QSAR studies can be done to determine the drug's potency and toxicity. So the Homo Lumo energy, see, it is playing a very important role, right? Okay, so here today we will be demonstrating the Homo Lumo energies. We'll be calculating that using Mopac. So first of all, we are going to construct a benzene molecule using Avogadro software. Yeah, it's a molecular visualizer and an editor. So we use it, then we optimize it to bring to the stable geometry. Then we will be performing a PM6 calculation using Mopac by using the word graph F. Okay, we will see what this graph F means in the demonstration. Okay, then you see for Mopac output you will be getting, and you can get the details about the Homo Lumo energies from the output data. And finally we will be visualizing the molecular orbitals using JMOL, molecular visualizer and editor again, and we will get the Homo Lumo energy data and the electron occupancy and everything. So a lot of information we are going to get from this. So let's go to the demonstration now. Okay, we have to go to the Avogadro and you just using the draw thing, you just draw a benzene. So I just take benzene as my example. So I just draw it with 6 carbons and fix the double bonds wherever necessary. Yes, and now you just adjust the hydrogens, click on each carbon and you get your hydrogens. Yeah, 6 carbon and 6 hydrogen, your benzene is ready. Now you need to optimize it. Choose the optimization tool, select the force field as mmff94s since it's an organic molecule, and start till your D is equal to 0. Energy minimization has been done, and finally go to extensions and click Mopac since we are going to run a Mopac calculation. I'll just change the title to C6H6.mop. So I choose geometry optimization as calculation. It's a neutral molecule, so charge is 0, Cartesian. The method is PM6 and multiplicity is singlet because all electrons are paired. And this is your code which is default. I'll just remove that ox large and change it to graph F. This is very important. You have to put graph F. Only then you can visualize your molecular orbital. Charge equal to 0 represents no charge on the molecule. Singlet represents that all electrons are paired, and PM6 is the Hamiltonian which you are going to use for this calculation, and these are your Cartesian coordinates, and click generate. Yes, you have the file name. You can save the file in your required location. I'll just save C6H6.mop. MOP is the extension for this, okay, because it's Mopac calculation. Yeah, now all has been done. Now you just go there to your saved file, click and drag the file onto the desktop Mopac icon, and see you'll be generating some 3 files, okay, out, ARC and MGF file. ARC file and out. If you click the out file, you can see all the calculations which have been running, all the Mopac calculations you have seen previously in the previous videos. So all calculations are shown here. You can find the Homo Lumo energies. The number of filled levels is 15, and you have the MGF file, right? Only when you put graph F you will get the MGF file. You need a JMOL to visualize the molecular orbital, okay. By the time you would have installed JMOL. Now I'll just click and drag the MGF file and place it over the JMOL, and you find your benzene molecule display in the JMOL. JMOL is a Java program, so it's inbuilt with Java. Now I click console, and you find you have 16 molecular orbitals. Okay, to get console window you should right click and then select console. Now we have 16 molecular orbitals. So I'll just change background to white. Yes, you have white. 16 molecular orbitals, right? So I'll just give the command like this, MO1. Yeah, see, you can see the MO1 over here, and also you can see the occupancy is 2, which represents 2 electrons are occupied in that particular MO molecular orbital, and its energy is negative, which indicates that it is a HOMO. It's a HOMO energy. We'll give MO2. Yes, you get it. Occupancy 2. Again, energy is negative. And MO3. See, you can visualize all the MOs. It's a Java program and a GUI, so you can use it. Graphical user interface to visualize it, right? MO4. Then I'll give MO fill no mesh, which means you can see that wire like arrangement is gone and everything is filled, right? So it's MO fill no mesh. Then I put MO translucent, and click enter. MO translucent, I think spelling is wrong. I'll just change it. Yeah, it's correct now. And now just click enter. Yes, you can see the molecules and atoms inside that MO. And I go on putting more things like MO4, and yeah, you can see it. See, O2 electrons occupied and still HOMO. MO5, yes, you can see 2 electrons occupied, energy is negative, HOMO energy. And see MO6 negative energy, occupancy 2. MO7, yes, it's 2, and the HOMO, still it's HOMO only, HOMO energy. MO9, yes, same negative energy there. MO10, yes, the same negative energy. Then yeah, you can see the occupancy is 0 and the energy is changed to positive, right? Which indicates the LUMO has started. It's the LUMO orbital, right? So see, till your MO9, I think so, we got negative energy, which is your HOMO energies. And after 10, you see, you get occupancy 0, no electrons is there, and the energy is positive, which indicates it's a LUMO energy. And see the MO0 again, positive LUMO. So now till that 16 molecular orbital, it's LUMO only. Okay. See how you can identify with the data displayed on your JMOL Java. MO15, and you have MO16. Yeah, see LUMO, and it's the energies keep on increasing, right from negative to high positive value, which is a HOMO to LUMO. See MO17 I put, and it's a script error because only 16 molecular orbitals are there. When I go beyond it, it shows an error, right? Only 1 to 16 is required. It's showing the data like that. If I put I'll just try putting the snow mesh again. Let's see what happens. I think okay, nothing has been changed because MO translucent is used already. So when I put MO fill no mesh again, it will not show. So either you have to delete over there and put again so that it will be able to do, or if you have MO17, no, so it will not show. That's it. Okay, thank you.